Right, on to the second short video on this idea of maximum intensity projections as a starting point for looking at these angiograms. So I'm now in MATLAB. In the first video, we looked at these MRAs, these MR angiograms in fossil eyes. But for some analysis, we probably want to move into MATLAB, so it's worthwhile for making figures and so on to also be happy in here. So you have access to this code in the repository. I will show you at some point how to get hold of it if you have any problems, but it should be relatively straightforward. The only other thing you should know for my particular setup, which might be a little bit different for you, is that I've got these shortcuts to a folder called Angio and another one called Atlas, which points directly at a folder that I'm sharing in Teams. So it's a little bit easier to with the path names to the data files, right? So you can, if we move over to the left-hand side here to this script, you can see that I declare a variable here called fname, file name, which points to the folder angio and a file called angio_brain.nir in that folder. Okay, so it just makes the path names a bit nicer. There's other ways to get around that too, but I just found it's the easiest. Okay, so just before I get started, I just want to make sure that I don't have any leftover bits from what I've been doing in MATLAB before. So I'm going to type clear all, that clears the memory of MATLAB. And now if I just type who, you can see that would usually show any variables that are defined in the workspace. There's nothing there at the moment, just to show you that I'm starting with a clean slate. Okay, so what I'm going to do here is I'm going to write my scripts in such a way that I start everything with 2% signs in the comments when I want to start a new section here, which makes it quite easy to run through. You should have probably seen this before as well. And so I can now run this section. There's actually a shortcut on the Mac, which is Command Enter, and presumably on the PC it's Control Enter, and you can actually, I will often not move the mouse up here, I'll just hit the buttons and you can hear me and it will execute that bit of code, okay? So I'm going to press that button to run the section, and it looks like nothing has actually, it says it's busy, but it looks like nothing has happened. But if I type who again, you can see there are now 3 variables, okay? Fname was defined, D actually loads in the whole data cube, right? It's a 3-dimensional image, so we can look at how big that is, size of D. You can see it's 672 by 672 by 160 voxels, so quite a big cube of data. And also I stored this variable called HDR, which contains information about the header, and you will see why that's interesting in a second, okay? HDR, all of the metadata that actually comes along with this, you know, when size, pixel dimensions, and so on and so forth, okay? So before moving forward, actually, I'm going to grab some information that's going to be useful later on for when I play around with this particular data set. And one thing that we want to know for sure is how big is this image, okay? So we want to store that information in a variable so we can use it again. And then the other thing that's important for visualizing things correctly is the pixel dimensions, right? So in this particular case, the images and the voxels aren't the equal size. Okay, so you can actually look here, if you read through the information of all of those and look at pixel dimensions, you can see that some of the dimensions, right, the first and the second dimension, pixels are 0.2976 millimeters big within the slice, but the slice thickness was 1 millimeter, okay? So they're actually not cubes, they're little cuboids, they're sort of squished cubes. Actually, I guess stretched cubes, if you think about it, squished in two directions. And if you want to display them correctly, as you slice through this data cube in different orientations, you need to remember that this is the case, okay? So I'm going to run that section as well. So now I'm actually going to run through, I'll just run the code and then I'll unpack what's going on here. So you have access to this before, maybe you've already looked at this, okay? So it's going to run through a loop of stuff and it produces these 3 images, okay? So what are these images? What are we looking at? These are actually the maximum intensity projections through that image, okay? Through the 3D image. So the only thing we've done is we've walked to different sides of the cube, and we've looked through the cube and looking for the highest intensity value along that orientation. We've recorded all of that, and we end up with a two-dimensional image in one orientation, the third one, right? So this would be essentially on three sides of a cube that are orthogonal to each other, okay? And you can see that there's quite a lot of structure visible in these things. And so those are the things we want to be playing around with and trying to identify what certain structures are in here. And ultimately, in a person with a healthy or diseased brain, you might want to be able to tell the difference between these structures, right? So if there's some disease, you know, there might be some malformations in the arteries, or some clots in a stroke, for example. You might have lost certain arteries after they've been clotted off. This is the place where you want to look for that kind of information, okay? So there's some toolboxes and various tools out in the world, and we'll actually, over the next couple of weeks, we'll try and explore some of them, so we don't have to start all of the hard work for doing this analysis on these kinds of images from scratch. But I think it's important that you understand what the basic data are actually about, okay? So I don't want to make this too long, but I just wanted to show you one of the helper functions that I've used here in order to actually get the maximum intensity projections out. Okay, so in the first video, I explained to you the idea of how this maximum intensity projection actually happens. Okay, so just to reiterate, so let me do home here so we get a little bit of space in the window here. Let's, just for illustration here in the command window, make a two-dimensional bunch of numbers, a matrix, and let's think about how the maximum intensity projection in that two-dimensional case actually works, okay? So I'm just going to say x is equal to rand, and let's make it not exactly a square image, so you can see what's actually going on. So I'm going to make that 10 by 20 pixels big, okay? So you should probably, if you've forgotten what the convention is for the sizes, try and remind yourself, okay? So does that mean 10 rows and 20 columns, or 10 columns and 20 rows, okay? Just think about that for a second. Right, so the convention is we talk about rows first, then columns, and the third dimension. So what I've defined here is a matrix that has 10 rows and 20 columns, okay? And you may remember that I can take the maximum of that column, and it will do something, not just find the maximum number in that whole thing, but it will do it in a particular way, okay? So in this case, it actually gives me an answer back that's 20 columns wide, okay? So what it's done is, by calling max on this table of numbers, it's actually done this calculation for each of the columns at a time, and it's given me a number back, okay? So this is actually a maximum intensity projection through that table of numbers, okay? So you can convince yourself, maybe with a small example, that the 0.9694 is the largest number in column number 1 of this data set, okay? So you can actually see it probably here, and you can sort of go through and see whether MATLAB is lying to you. 0.9706 should be the largest number in the second column. It may be in a different row, but that's the whole point of finding the maximum, okay? So this is the way in which the maximum intensity projection actually works, okay? So, but we only get one orientation of this thing out. So the trick to remember is that lots of these operations, like max, the mean as well, standard deviation, various other mathematical operations you can do, you can specify the dimension in which you want to do this, okay? Now, there's a little gotcha, which is that maximum also accepts potentially a second argument, okay, for comparison. So probably worth reading through the help of this if you find this a little bit confusing at the moment. But if you look here through the help and just quickly scan through all of the different entries, you see that there's an option for specifying the dimension, And if we only want to do it to one table of numbers without comparing things, we need to give it an empty argument as a second input. Okay, so just to go back, if I want to just take the max in dimension 1, I can leave it off, right? So this is the way to do it. Or if you want to be explicit about being along dimension 1, this is the way to call it. Okay, and so now by analogy, you could imagine what it's like to do this in the second dimension, right? So what's the number I would have to change here? Well, it's not the, it's not dimension 1. I want to do it along dimension 2. And before I hit return, just think about what is the expectation of the output now, okay? Given that this is 10 rows by 20 columns, and we're now taking the maximum number across the columns, so along the rows in this particular case, right? What do you expect that output size to be, right? How big is it? It's not 20 numbers, right? It should be 10 numbers. And the orientation in which it comes out should be different, right? Because we're now going across the or opposite the other orientation in this table. So I'm expecting a sort of a column vector of numbers to come out. And sure enough, that's what it is. And there's 10 of them because we have 10 rows along which we're operating, okay? So this is the two-dimensional version of this maximum intensity projection. If X was three-dimensional, then when we did this trick of doing 1, 2, and 3, we could essentially get the maximum of all of the slices, of all of the pixels for a particular slice in 3 dimensions. And this may sort of ring some bells with you, because it's actually quite similar to something we did in one of our lab classes, which is sort of selecting a slice out of a cube of data. And so the reason I'm telling you about this is because I've actually written, because this operation of taking this intensity projection in different orientations is something that we might want to do again and again. I actually wrote a little helper function, and by analogy to return slice, which is a function we wrote in the autumn term, I wrote this. I changed it to a function called return mip, right? And if we look at this particular case here, you can see that it accepts the whole array across which we want to do this maximum intensity projection. For now, I've kept it relatively simple, right? So you probably remember some of my pet peeves about how the documentation and the help section should be, so we should probably fix that. I haven't included when I wrote it. It doesn't have a complete explanation of what's going on here, but this is just to check that it was actually working while I was hacking this up. I'm also not checking that the input is only 3-dimensional, so if somebody gives us a 4 or 5-dimensional input image, that might actually cause some problems. But you can see here that for a particular orientation, which could be 1, 2, or 3, I'm calling this max operation in 3 different orientations, okay? And as you may remember, because when we are selecting out dimensions in an array in a particular orientation, we sometimes are left with single dimensions in places in between the beginning and the end. We need to do this squeeze trick. Okay, so if this doesn't ring a bell, maybe go back over some materials from the autumn term and the assignment, or ask me the next time. Okay, so this is how this actually works. Okay, so I'm going to stop this recording here because this seems quite a nice chunk. Before I let you go, just think about some of the things that you might want to double check here. So is the color map maybe the best to look at? How could we change the contrast in this image in the sense of maybe giving us slightly better differentiation between the brightest and the darkest bits in the image? How could we highlight things here? How can we add some text information to help us get oriented in this display a little bit better? Various other kinds of ideas of how you might want to play around with this. Okay. I'll stop the recording here, and in the next little video, we'll explore some of these ideas further.